So once again, as our class started, we'll have a set of mini drills for you to develop proficiency with the CIDR method. Today's lightning credit, you must break out a /24 network for better efficiency using the CIDR method so that each of the subnets formed uses a /27 subnet mask. That means we're sliding it 3 places to the right. We're taking a network that has 256 network addresses, 253 are usable. 3 are taken up by the network ID, the gateway, and broadcast. So there's 253 usable network addresses, and we have to break them down into smaller networks for more efficient use. By sliding the CIDR subnet mask 3 places to the right, 2 to the third is 8. We're splitting that network down into 8 smaller networks, each with 32 addresses. 32 addresses, 3 of those are taken up, 1 by the network ID, 1 by gateway, and 1 by the broadcast address. Broadcast address is used by Arp. We'll be talking about that shortly. In any case, you have 29 usable addresses. How do you find the answer to this? Well, if you're going from 24 to 27, what you're going to do is open up your /27 template. Hopefully you've had those downloaded by now. When you start with a 24 and you move to a /27, the mask increases by 3. The number of networks you create are 8 usable networks from a single network. The CIDR multiple is 32, meaning the number of addresses created is 32 addresses. Each network has to have a network ID, a gateway, and a broadcast address. So if you subtract those 3 addresses from 32, you get 29 usable hosts. My address ends in 101. So from the original network, this client, the network address is originally 202.97.196, but the client address is 101. Where does 101 fall on this table? Well, the first usable address and the last usable address would be this network here, network number 4, because 101 falls between 98 and 126. Therefore, the answer I'm looking for is the network ID is a .96/27, the gateway is a 97, and the broadcast is 127. Let's see, 96, 97, 127. The other choices were .0, .1, .31, .192, .196. Actually, if you put a 101 address inside either this network or that network, it won't know how to talk, because the address range isn't in the usable address range. So I'm going to select this answer. I'm going to save and submit. And hopefully I should have had a correct answer. That's the one I selected, right? Well, I'm going to go in and look at each of your answers, and if this thing scored incorrectly, I'll go ahead and adjust the credit. But whatever it is you chose in the time allotted, we'll figure out. That is the correct answer. I'm not sure why that's scoring incorrectly. Maybe because it's late. Is that why? Let me look at this. Oh, hold on. Oh, this was a multi-answer instead of multiple choice. Okay, so here's what I'm going to do. I'm going to choose this answer as the correct answer. I'm going to submit and update attempts. There we go. All right, so that'll score everybody's question correctly. It should have been a multiple choice question instead of a multiple answer question. And if you go back in and you look at what your score is, you either got it right if you chose this, or you got it wrong if you chose one of the other two. Are there any questions about the CIDR challenge? On Monday, we'll have 2. On Wednesday, we're going to mix it up. We're going to be doing some other things with CIDR. Well, we're going to be doing something with CIDR on Wednesday, and with ARP, and with DNS. So you'll have some lightning credit rounds on Monday and Wednesday. Any questions about what we've done to this point?
No questions.
No questions.
Okay. Today we're going to finish our review of IPv6 essentials. And then we're going to try to get a big picture for how all of the different network layers work together interactively, so that you know how to troubleshoot, issues. Yeah, I would figure that I'm just getting started, and then so it pops in. All right, so we will have a study guide addendum for this module. And essentially what we want to do is finish where we started getting into IPv6. So remember, there are 3 major innovations that help us deal with network resource challenges. The first one being NAT, the second one being CIDR, and the third one being IPv6. We started talking about the differences between IPv4 and IPv6. We called special attention to the double colon. Now, the double colon is used to write a shorter address. So if you have a very long 128-bit 32 hex character address, in many cases with new implementations of IPv6, not many of those have been deployed, so there's just a few characters that are used on the front end. Remember that in an IPv6 address, all 64 of the first addresses, all 64 of the first characters, the first 64 bits, are used to define the network ID. And there's 2 components to the network ID. One that has to do with the organization worldwide, and the other one that has to do with the geographic location, right? So basically, I think it's 32 bits. Well, wait a minute here. "48 bits is for the organization, and then 16 bits tell you what location in that organization." So IPv6 can be used for very large organizations, multinational corporations, international organizations, right? So you have 48 bits to specify the organization, and then 16 whole bits to specify 65,536 separate locations. How do I know that? If I have 16 bits for a singular organization, if I have a single organization defined by the first 48-bit component, after we've defined the organization, I can use the next 16 bits to define which location in that organization the network is operating. 2 to the 16th, if I get my calculator out, is 65,536. So it's a huge address range. And then the next 64 bits define the client at that location. If you have 64 bits at a specific location to define individual networked clients, well, let's see just how much that is. 2 y to the x 64. Okay, that's million, billion, trillion, quadrillion, 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,616 network clients can be supported at each location. Woohoo! I don't think we're going to run out of network addresses. Not on planet Earth anyway. We mentioned that loopback is real simple. The double dot and the 1 means that there's 127 zeros before that 1 when you're using IPv6. Remember that the double dotted notation, the double colon notation, can only be used once. So this combination right here is not a valid IPv6 address per the specification. Any questions so far? Any questions?
So far, so good. I'm good.
Okay. We talked about the multi-purpose unicast versus multicast. So if something is streaming live with IPv4 networks, like the inauguration, if that's streaming live and everybody that's receiving that broadcast is getting the same stream of bits, that's a multicast address. If you're using Netflix to pull down a movie on demand, and that's different than the person next to you who's watching a different program, but that's a unicast application, okay? And that's as far as IPv4 goes. In IPv6, you have 3 different multicast types. You have a unicast, which is point-to-point on demand. You have multicast, just like IPv6, but then you also have anycast, which means you can deliver packets to the closest, to or from the closest client nearby. What are we saying? It's like a peer-to-peer arrangement. It's like BitTorrent on steroids. When we talk about DNS, I'm going to mention in a minute about DNS. Domain name service is one of 3 interactive networking services that operate across the IP stack, protocol stack, at the application layer. Basically, a glue record glues a client IP address with a client name. The device or system has a name, and it's assigned an IP network address. And there's a record that glues the name, quite literally glues, sticks the IP address numerical value with the name of the system or device. That glue record is also called an A record or host record. Okay? So a glue record is also called an A record or a host record. Those records are organized into sets based on domain names. And if you have a set of records with the same domain name, that's called a zone. We'll get into that more. IPv6 does the same thing with DNS, but it has a quad A record because, well, it has 4 times the IP address space. So instead of just having a 32-bit IP address, it has a 128-bit IP address, which takes 4 times the network address space to articulate or define as a regular IPv4 domain name record. So remember that when we're talking about DNS and IPv6, that's a quad A record or host record or glue record. Says that IPv4 uses broadcast with address resolution protocol to bind a MAC address value for a network interface. What are we saying? If I look at this, can everybody see my screen?
Yep.
Yeah.
On the physical network interface layer, on the data link layer, layer 2, my network interface card, my wireless network interface card has a media access control identity. I like to call it The physical address, I like to call it a MAC identity, because this is like a fingerprint. There are supposed to be no two MAC addresses the same on the planet, right? So even though it's a physical address of the physical network interface on the data link layer, right? The media access layer, where the data cable links to the card, right? Or the wireless signal links to the Wi-Fi card. This media access control identity or physical address has to be associated with an IP address. So on layer 2, where we're broadcasting either Wi-Fi or Ethernet, it is a broadcast technology. Everybody that's connected on the same local area network shouts at each other at the same time. If we were all to start talking simultaneously, if all 11 of us were to begin talking at the same time, and we all started broadcasting, speaking audibly outward to try to speak with different people at the same time in the same airspace, you'd get a cacophony that sounds like a flock of geese that are all honking, and nobody would be able to make any sense of anything anybody's saying. What happens on the broadcast layer is that there's an organized way to take turns broadcasting, and essentially every time somebody broadcasts, they're putting out a frame with someone else's MAC address so that the other person can say, oh, that's my MAC address, I'm going to listen to this. And everybody else is supposed to have the good sense not to listen to it, because their network interface card doesn't have that identity. So when Lance's identity is queued up for a broadcast, Lance says, hey, that's my physical address. Lance's network card cues in and listens. Everybody else's card is supposed to say, okay, that's not for me, and I'm not going to listen. That's what happens on layer 2 with frames, either Wi-Fi or Ethernet. When people are networking, that's what's supposed to happen. When all of this stuff is happening too much, there's contention and collision. It's called network contention or network collisions. And what's supposed to happen is that the Arp table is supposed to help associate a physical network port with a MAC address, and on a switch instead of a hub, when somebody queues up Lance's MAC address, only Lance's physical port on the switch gets that frame. Nobody else's gets the same frame. So on a hub or on Wi-Fi, everybody hears everybody, everybody sees everybody. It's a mess. With a switch says, oh, I'm going to switch to Lance's port because that's his MAC address. So it associates this MAC address with a physical port on the switch. But the Arp table also associates a MAC address with an IP address, because you don't want to just talk on the local area network. You want to talk beyond the local area network. Any questions so far about what happens with ARP? Any questions?
None so far.
No questions.
Okay, so I'm going to queue up our addendum. Well, actually, before we get into that, I do want to take a minute to share with you. All right, so I'm going to post an assignment, a formal assignment for using, for breaking down into smaller subnets. And I'm also going to post an assignment for creating a larger subnet using CIDR, okay? So you can also work CIDR in the other direction. Instead of sliding the subnet mask to the right, you slide it to the left to create a larger network or a supernet. Not a subnet, but a supernet. That's the proper term. If we're using CIDR to create a larger network because we want to do that efficiently without burning up extra network addresses needlessly, we want to get away from class-based networks. If we can only slide from 24 to 16, we're jumping from 256 addresses to 65,536 addresses. to, I don't know how many millions of addresses on a /8, right? Just too wasteful to use class-based networking. So we're going to slide in the other direction. And by sliding in the other direction, we're going to, we're going to create a supernet out of the subnets. So we're taking multiple smaller subnets and combining them into a supernet. When we slide the CIDR net mask in the other direction, what we're going to do is post this as an assignment in Blackboard. So there's two assignments. One where you're using CIDR to create a greater number of smaller networks. You're breaking out a larger network into a greater number of smaller networks, and you're sliding the subnet mask to the right. And then there's also going to be a separate assignment for creating supernets, larger networks using CIDR, which is more efficient. The best way to do that is to use this website. What you're going to do is type in this information, and then you're going to slide it 2 places to the left. So now it's a /14. Notice in this method, when we're increasing the size of a network using CIDR, instead of the number getting smaller, the number of ones is actually, well, the number of ones is getting smaller, so the subnet is actually getting bigger, right? So as the number of ones decreases, the size of the network is increasing, right? So this is a class B network normally. I don't want to slide all the way to a /8. Oh my gosh, I don't need millions of addresses, but I need more than 65,000. So I'm going to take this information, I'm going to plug it in here, and I'm going to show you how this works right now. So I'm going to go to this website, and I want you to do the same thing that I'm doing. And this handy dandy, all right, so DE means German. Jodi's is a German engineer, and that's actually a very helpful thing. As we did before, you have to note the original client address, right? So in this problem that we're doing, where we're taking a 135.217.86.155 address in a /16 network, we're going to slide the subnet mask 2 places to the left, which decreased. Now there's only 14 ones in the subnet mask. I need to note this original client address because I need to find out where it fits in the breakout that results. I'll show you here. So I'm going to right-click this and copy that number and go to the website. Whoops, where are we? I'm pasting this in here. So it was a /16, and I'm going to move it to a /14, and I'm going to calculate. And what you see is what it shows the original. It shows the original network ID. So this first set of results is the original network ID. So it takes out these 2 octets and it says, okay, here's what you had originally for the network ID. But now if you slide to 14, it takes that 255.255.0.0 subnet mask, and that becomes a 255.252.0.0 subnet mask. So it's going to create a network, right? A larger network. And the new network, when you move this thing back, instead of starting at 217, right? It's not 135.217.0.0. The new network ID is 135.216. Hello. That number changed. So now The new network ID is 135.216.0.0/14. Moving in the other direction manually, if I basically tried to give you slash tables for moving in the other direction, it would be trickier to calculate in Excel, right? It'd be trickier to break out in Excel. So just remember, you're using these slash templates when you're going in the other direction, creating smaller subnets. But when you're going larger, you're going to use this website. And this website's going to do an efficient job of finding or determining the new network identity. And that happens to include the original client address. So the original client address, 135.217.86.155, fits neatly in this network. The broadcast address, look at this. The broadcast address is 219, right? That's huge. Up here, the original broadcast address was 135.217.255.255. If we stick with class-based networking, that's the broadcast address for the original network. But if we supernet, what we have is 135.219.255.255. The broadcast address always ends in a series of ones, right? So you still end up with all ones on the end of that chain. So we're dealing with 14 binary values that determine how the network is broken out. Look at the number of networks, hosts that can be accommodated. In this case, 65,534. It counts 2 off for the network ID and the broadcast. So it's actually 536. But if you designate the first one for the network ID, 0.0, and the last one for the broadcast address, then 2 of those addresses that are 65,536 large become 65,534 usable addresses, right? This website doesn't designate a gateway address. Gateway addresses are usually determined locally, and they usually make it one more than the network, but there's nothing to prevent a network administrator from saying, yeah, I don't want to use the very next number to be the gateway address. I want to flip it instead and make the gateway 254 instead of 255. So it's one removed from the broadcast. Sometimes people do that kind of goofy stuff. When you think about it, the broadcast address is just one binary digit away from the gateway address, and very strange things start to happen when people just ad lib like that. But the important point to understand is that I've slid the subnet mask 2 places to the left. That increases the size of my network by 4. And if I do the math, 65,536 times 4 is actually 262,144 addresses. It says 142 because, well, Jody has accounted for the network ID and the broadcast address. So there's 2 less. That's the number of hosts you can accommodate, 262,142 if you supernet. Any questions about what you're supposed to do for your supernetting CIDR assignment? It's pretty easy. You just plug in the address, the original net mask, and the final net mask, and then you're going to highlight these numbers, get a screenshot. That's what you're going to do. For each of the solutions you have to determine. Okay?
Okay.
Any questions?
Sorry, I
No
came a
question.
bit late. Will you be uploading this video to
Yep.
Blackboard soon?
Yes, as soon as we finish, I'll upload it to Blackboard. If you look, I think the one we did Wednesday is out there. If you look in resources, inside session recordings. Oh, I do have it in YouTube. I'll post it from Wednesday and today. Okay.
All right.
Okay, so I want to talk about the rest of this IPv6 stuff. It's really important to understand that IPv6 does not use a subnet mask. CIDR, sliding the subnet mask bits, none of that. You don't have a subnet mask. You don't have a subnet mask per se. You always use the first 64 bits for the network value. You always use the last 64 bits for the client value. In IPv6, you don't slide either way. You don't use ARP either. So you don't have this broadcast protocol that uses frames. It takes advantage of multicast and a built-in service called network discovery, IPv6 network discovery. The service defines a multicast address all clients must listen to, and then directs the neighbors to reply, right? So the answer back from neighbors contains the MAC address values of the neighbors. So ARP is replaced by network discovery, and that's how MAC addresses are communicated to other clients. Here are some other things you need to know about IPv6. One of the toughest things to do is to navigate with a web browser to an IPv6 network resource, because instead of just using an IP version 4 network address, let's say you don't have the name, you could just put HTTP, and you could put 8.8.8.8, and you're at Google. Or actually, technically, that's the Google DNS server. But the point is that you can do all those interesting things. If you're dealing with an IPv6 address, you basically put it inside square brackets. So you put it inside square brackets, all right? Any questions? So normally you'd put like 202.96.43.197 if you didn't have the domain name, and you could go directly to that web server based on the IP address. What happens with IPv6? You do the same thing. You just take the IPv6 address and put it inside square brackets. You have to put it inside the square bracket. Open and close square brackets. Any question about how to use IPv6 addresses in a web ad in a HTTP URL?
No questions.
Okay. Here's another thing you need to do. We have this convention of hitting named resources on a network. It's called the Uniform Naming Convention. So it's a little bit like what you do with the web browser when you're putting in a URL, a universal resource locator, and it says HTTP, whatever, blah, 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 Google, Facebook, you know, Netscape, whatever. You put all those things in there. In older networks, you had this / host name, and then you'd have another / and then a drive letter. So you connect to network resources by forming what's known as a drive map using the uniform naming convention. So instead of saying HTTP, you go /. So these are forward slashes with URLs. We're using backslashes with uniform naming conventions, right? With IPv4 addresses, if you don't know the host name because your DNS or your host's record is barfed, you can use the regular IP address instead. What do you do if you have an IPv6 host? You substitute the colon symbol with a dash. So this is the normal expression of an IPv6 address. When you use it in a UNC to map to a drive letter with IPv6, you take all the colons out and you substitute with dashes. So you have a //2001 dash, DB8 dash, instead of a 2001 colon DB8 colon whatever. Does everybody understand what I'm saying here?
Yeah.
This is huge. Every single IPv6 device or client or system is assigned a local link. The local client address. If I ask you, what kind of address is this? And it starts with FE80, that is the local system address, local link system address, the LAN address, the client address in the local network, okay? So if you see anything that starts with FE80 with IPv6, it means that it's a local address on the network. If it doesn't have FE80, it's a different kind of IPv6 address. Multicast always starts with FF0, and then there's some number where X is 1 through 8. So it's FF01, 02, 03, 04, 05, 06, 07, 08. Okay, those are multicast, right? If you're having streaming media. All right, so let's take a short pause here and let's jump over to our addendum. So there are some things that I wanted to help you. I wanted to walk through how the different layer protocols interact with each other, starting with layer 2, okay? So you have to know about ARP, DHCP, and DNS, what they do at which level, and how they interact with each other, okay? So if any of these aren't working properly, you cannot connect or communicate on an IP network. So understanding how these work and what they do is useful when you're trying to troubleshoot a network. So we'll start with layer 2, okay? ARP works on layer 2, either with Wi-Fi broadcast or Ethernet broadcast. And it associates the MAC identities, the physical address, right? Or the MAC identities with IP addresses on layer 3. So when we're talking about associating MAC to IP, we're talking about ARP, okay? Once the IP layer is active and enabled, a DHCP server on the local area network listens for a DHCP request. If you have a client that is set up to automatically receive an address, if I get an IP address automatically, and that's what most people do. We'll talk about static addresses here in a minute. Automatic addresses, everybody just has it set on automatic. You get an automatic IP address and it's assigned by a DHCP server. You're saying, well, I don't have a DHCP server running in my house. Yeah, you do. You have a DHCP server running on your wireless access router. It also gives you which DNS servers to use, right? So the DHCP server listens for the ARP broadcast. It's listening for a client that connects. When the client first connects, it's going to go, hey, I need an IP address, right? If it's set to automatic, that's what it's going to do. As it's set to automatic and DHCP says, okay, here, use this IP address. It'll pick an address that is not supposed to be used by anybody else. Remember that you cannot have the same IP address on any local area network, because if you do use the same IP address for any two interfaces on the same network, boom, everything crashes, right? In any case, DHCP is the one that says, okay, you're going to get this IP address. Now you have an IP address you can associate with MAC. So it responds with the IP address lease. So it's literally leased. That address is temporarily assigned or leased. It is not permanently assigned. It is leased. and reused. And once that happens, and it issues that information, including which DNS server to use, then ARP says, okay, now I know the MAC identity and the IP address. So this has to play out just as I described it. ARP is listening. Somebody connects to Wi-Fi or Ethernet. When they connect, they say, hey, I need an address. That's a DHCP request. The DHCP server says, okay, here's an IP address. Once that DHCP server assigns the address, then you suddenly have the means to complete the Arp table entry. So what happens is that this information is stored in the Arp table on layer 2. So the switch or the Wi-Fi equipment stores this association between MAC address and IP address. So this is a media access control identity, and this is a network address. It's stored in the Arp table. You can view the Arp table by typing a command from the prompt, right? I think it's show Arp or something like that. It's very simple. But you can see what's in your own Arp table. Every client has its own Arp table, but most switches and hubs and wireless routers have their own Arp table. It associates layer 2 with layer 3 information. And that's important. Now, DHCP can also work with DNS to automatically associate the client or device name with its unique IP network address. So if you're talking about device name to IP network address, that's called a DNS registration. So when a client connects and it receives its information, now it knows which DNS server to use. It got that from the DHCP server. It says to that DNS server, oh, my name is, my client name, my system name, my device name is, and it registers the IP address with that name. DNS is used for any network resources that are referenced by name, either URL or UNC. We just talked about that. DNS servers manage a special record that glues a name to an IP address. It's called a glue record. Collectively, if these are associated within the same domain name, the set of records are called a zone. So if I say table, I'm talking ARP on layer 2. If I say zone, I'm talking about the application layer. DNS operates on the application layer. Now, here's one thing that I should have highlighted. Where is it? The DHCP zone. No, scope. So the number of addresses, right? So what do you call the address range a DHCP server can issue? That's called a scope. So if we say table, we're talking about ARP layer 2 broadcast. If we talk about a scope, we're talking about the pool of network addresses a DHCP server has to issue to people that need them automatically, right? It automatically issues them. That's called a scope. If we talk about a zone, we're talking about DNS. You need to understand each of those terms interactively, right? So a set of records together, a set of DHCP addresses together, okay? It's a scope of addresses, a table of MAC identities, and a zone of host or glue records. Those are specific names that you need to associate with each level. ARP and MAC occur on layer 2. IP address assignment and scopes occurs on layer 3. DNS associations for name to IP address occurs on the application layer. So if you're using the internet protocol layer, that's layer 5. If you're using OSI, that's layer 7. A lot of times when something misfires, it's because one of these processes renews or refreshes. The important thing to understand is that we're often reusing or recycling network resources. ARP is reusing and recycling associations between connected devices and the IP address range. DHCP is reusing IP addresses as clients come on and off a network. You may have a case where you have a shopping mall, you have 256 addresses, but you could have 5,000 people that come and go to that shopping center in a week. And you run out of addresses. So you have to recycle the IP addresses, and no two can be the same, or something crashes, right? So usually what happens when network isn't functioning properly, it's because one of these processes doesn't update correctly, okay? Another thing that happens with a misfire that can be resolved very easily is that a lot of times you can use the fully qualified domain name as opposed to just the host name. A lot of times when you're trying to hit something on a network, if I have a server named Titan, but I have an organization called Team Titan, why? Oh, I don't know, because I was tortured for years while my sons growing up watched Team Titan. I hope you're smiling now. In any case, I just want to see if you were paying attention. Okay, so if I have a server named Titan, right, and it's part of a DNS zone called team.org, so, you know, it's a domain name, right, team.org, and there's a zone associated with that, a collection of records. Titan could be one of the A records. If I use the fully qualified domain name, this is called an FQDN, by the way. If you see the reference to FQDN, it's talking about the fully qualified domain name. This is a fully qualified domain name. This is not. This is just the host name. A lot of times things will work if you just use the fully qualified domain name. Why am I telling you all this stuff? Because when you create network applications, you can specify as a part of your requirements for that application that the users have to use fully qualified domain names. And why would you want to use a fully qualified domain name? Because sometimes there are systems that reuse names. Every default name for an iPhone is iPhone. And the problem with that is, if that's a DNS record, and nobody changes their iPhone name from iPhone, you're going to have multiple iPhone names. So you got to make sure that that doesn't create a problem. Usually doesn't, except when you're dealing with servers. Sometimes DNS records change and update automatically, but the local DNS record stored in RAM does not. It hasn't been updated on the system. Usually using ipconfig flush DNS helps resolve these issues promptly. If a DNS record on the server in the zone is not correctly updated, then the command ipconfig register DNS will force the DNS server to store the latest IP address for that name. So those are three quick ways to resolve a problem. Use the fully qualified domain name. If that doesn't do the trick, flush the DNS. If that doesn't do the trick, then register DNS. And then things will start working. Now, when the DHCP lease, notice the terms. When I say lease, I'm talking about the IP address lease from the DHCP server. When that's half expired, it will attempt to renew the address to ensure seamless communications. For this reason, if you're in an environment where network changes abound, or the number of clients can fluctuate dramatically, like a university campus where 1,200 students show up and then they all go home, that's a huge change in the number of network clients. You need to set the DHCP lease times to a much shorter lease period, 4 hours or less. Otherwise, you run out of addresses. For stable, unchanging networks, you can use longer lease periods, 3 to 5 days. If you run out of DHCP assigned addresses, a lower lease time will make sure that they're recycled much sooner. Much sooner, right? Much sooner. Okay. Did you catch that? When a client is powered off, this is the part we're going to end on because we're right there at the end of the class. Did you catch that? When a client is powered off, it may still have a leased IP address that it is not using. This is a problem. Unless you configure your DHCP properly, the DNS properly, and the ARP properly. So for truly important systems, such as a server where you need to configure the DH server with a reservation to ensure the same address is assigned should the network card reset to automatic with driver updates. Normally you would take a server that's providing email or web or a database application, and you would assign a fixed IP address, a static, unchanging. You wouldn't assign it with DHCP. But if you're doing Windows update or Mac updates or Linux updates, sometimes when the network card drivers are updated, it automatically resets to automatic, meaning it's going to look for a DHCP server. If your server providing email to 2,000 university students suddenly gets a new address, nobody knows how to get their email. This really sucks. Is everybody with me still?
Yeah.
Okay, so what do? In the DHCP server, you take the IP address that you statically assigned to the email server, you create a DHCP reservation. So if it, for some stupid reason, updates its network card drivers and decides, oh, I'm going to get an automatic IP address, it's going to get the same statically assigned IP address, whether it's automatic or it's static. Either way, the address never changes. So the DNS record remains true. So when people go to get their email at mail.uvi.edu, it doesn't barf up, right? No other client address is used, so it will pick the same address from DHCP, even if it's automatic. This will save your skin. Network engineers, network applications often fail to include these simple things in the specifications. If you let an IT network jockey make you look bad as a software engineer, it's because you didn't specify some of these things when you're creating your network client. If you create network applications, you need to include as a part of your application design, install specifications that say, oh, use an FQDN. Oh, make sure that when you set up the server for this online resource, that you also configure a DHCP reservation with the same static address. That way, your software doesn't quit working because some network jockey didn't configure the network correctly. What's happening now in our territory is that there are very few truly qualified network technicians working our internet service and our networks everywhere. And they're making everybody look bad. And it's not your fault, but you need to know what to specify and insist on when you're talking with these people, especially when you design applications for online resources, right? You want to design a new cloud application. Everybody, it's so cool. You just want to make sure it works, whether somebody at this internet service provider or somebody at the other internet service provider is doing their job or not. So that's part of the relevance for what we're sharing here. Are there any questions about how ARP, DHCP, and DNS kind of interact with each other on the different layers to form this set of associations in memory? The MAC address to IP network address, then between the IP network address and the system name. So we know how to connect to a system on layer 2, layer 3, and the application layer, right? Using a name. If any of those pieces aren't working properly, it barfs. On Monday, we're going to talk about how to troubleshoot these. Okay, I'll give you some quick commands to identify. Oh, the ARP isn't working right. Oh, the DHCP isn't. We need this adjustment. Oh, there's no route. We didn't even talk about routes today. Okay, but you got to understand what happens on these different layers with the network, and that's part of the routing network. We're setting the stage for routable networks. Does anyone have any questions before we sign off? Going once. Going twice. Okay.